by Nicholas Fasano on high-power ultraviolet vortex beams generated from relativistic laser interacting with ultra-thin foil. Nicholas, if you're ready, why don't you continue?
Hello, everyone. Thank you for being here. My name's Nick. I'm from Princeton University, and today I'm happy to discuss some of our recent numerical simulation work involving vortex beam generation from relativistic laser interacting with an ultra-thin foil. And so vortex beams, such as the Laguerre-Gauss modes, which are solutions to the paraxial wave equation in cylindrical coordinates, are characterized by a twisted phase front and a null on-axis intensity, and are useful for several applications, such as in optical communications or for optical manipulations. While most of these applications have taken place in the infrared or visible wavelength regime, schemes have been proposed to realize intense short wavelength vortex beams, such as high harmonic generation from relativistic plasma mirrors driven by infrared vortex beams, which generate harmonics containing higher order vortex modes. In addition, theoretical work has shown that using circularly polarized lasers normally incident on a thick plasma mirror target or a preformed microaperture target also leads to the generation of harmonics containing higher order vortex modes. In this work, we use particle and cell simulations to demonstrate vortex beam generation with a circularly polarized laser interacting with an ultra-thin foil. So in general, the efficiency of harmonic generation is dependent on several parameters, such as the plasma density, N, which is the electron density normalized to the plasma critical density, the laser amplitude, A naught, the plasma thickness, the target thickness, D, which is normalized to the laser wavelength, as well as the pre-plasma gradient scale length, the pulse duration, the carry envelope phase for ultra-short pulses, the angle of incidence, as well as the spot size of the laser are also important for the efficiency. Harmonic generation from plasma mirrors is most efficient when the laser and plasma forces are closely balanced, which is difficult to achieve with present-day laser intensities for most solid density materials. And so an efficient way of generating efficient harmonic generation is to consider the ultra-thin foil regime, where the plasma thickness is an effective way of adjusting the plasma density, where in this ultra-thin foil regime, the efficiency of the process doesn't depend on N, D, or A naught separately, but rather through the similarity parameter N and D over A naught, which is a measure of the effective charge contained within the target, normalized to the laser amplitude. Important for us is that we are using circularly polarized lasers at normal incidence, which in a 1D geometry you ordinarily would not expect to see harmonic generation in this case. And that's because for a circularly polarized laser, the V by B force is a slowly varying function of the laser envelope, and therefore does not drive fast oscillations of the plasma surface. This is in contrast to a linearly polarized driving laser, which will drive fast oscillations of the plasma surface at twice the laser frequency. We demonstrate this using 1D particle and cell simulations, where here I plot the spectral intensity as a function of frequency for both the case of a linearly polarized driving laser and a circularly polarized driving laser at normal incidence. And we see here that for the circularly polarized driving laser, there is no harmonic generation, but there is efficient harmonic generation for the linearly polarized laser, which has been shown in general to follow a -10^3 parallel scaling in the ultra-thin foil. Now, it's also been shown before that using 2D or 3D simulations, that it is possible to generate harmonics using a circularly polarized laser by taking advantage of transverse effects. And so here I show a 2D particle and cell simulation demonstrating that it is possible to see harmonic generation because of these transverse effects. What's special about these harmonics is that they contain orbital angular momentum. That is, that in both the transmitted and reflected directions, the harmonics of vortex beams. So before discussing the properties of these vortex beams in more detail, I want to discuss the plasma dynamics leading up to the emission of this harmonics. And to do that, we use full 3D particle and cell simulations to model the transverse effects that shape the plasma target, which allow for harmonic generation. So what I plot here are results from the simulation of the electron density at 4 different snapshots as the laser is interacting with the plasma. where the time, so the plots are in the y-x plane, where x is a longitudinal coordinate, the direction of the laser propagation, where the laser propagates from left to right. And the time t equals 0 corresponds to when the center of the laser envelope is at the position x equals 0. What we see here is that at early times, the laser is primarily interacting with a flat, overdense plasma mirror, for which, just as in the 1D geometry, we do not expect to see any significant harmonic generation. However, as the laser pressure begins to rise, we see the onset of this surface denting effect, for which subsequent laser cycles will see locally an oblique interaction at positions off-axis from the laser axis. And for an obliquely incident circularly polarized laser, we do expect to see harmonic generation. In this case, it would be in the reflected direction. And as the laser pressure continues to build, and because we're using an ultra-thin foil, eventually we see the breakup of the target, for which then the laser primarily will be transmitted through the plasma. When we look at the transverse plane of the electron density, as I show here in the YZ plane, we see that after the foil has broken up, the laser primarily is propagating through a micron-sized aperture. During this time, the laser will drive electron oscillations at the rim of this aperture, which will lead to harmonic generation in the transmitted direction. Harmonic generation from both the surface denting effect in the reflected direction and by propagating through the micron-sized aperture in the transmitted direction have been studied before, and here we show that in the ultra-thin foil regime naturally leads to both effects. So now I'd like to discuss the properties of the beam in more detail, and first we look at the longitudinal profiles of the transmitted and reflected beams for both the fundamental and second harmonic, where, for example, the second harmonic is obtained by filtering between 1.5 and 2.5 times the laser frequency. And what we see here is that the fundamental beam still remains Gaussian, as was the driving laser. However, in contrast, the second harmonic beam contains higher order transverse structure, most notably with a null on-axis intensity. And I had mentioned previously that one characteristic of a vortex beam is the presence of a null on-axis intensity, but also the presence of these spiral phase fronts, where the spiral phase fronts arise from an azimuthal dependence of the phase and is characterized by the azimuthal index L, which is also sometimes referred to as the topological charge. And so to check for the presence of these spiral phase fronts, we look at the beam in the transverse plane. So plotted here in the ZY plane, I have both the reflected and transmitted beams for the fundamental second and third harmonics. And again, we see that for the fundamental beam, the profile remains largely Gaussian. And so we conclude that this fundamental beam does not contain any orbital angular momentum. It's not a vortex beam. In contrast, for the second and third harmonics, we do see the azimuthal dependence on the phase, where, for example, in the second harmonic, as the azimuthal angle is varied from -pi to pi, we see a 2 pi phase shift in the phase. And for the third harmonic, we see a 4 pi phase shift in the phase, which is indicative of a topological charge of order 1 for the second harmonic and 2 for the third harmonic, and in general, topological charge of n-1 for the nth harmonic. It's important to also note that all three harmonics remain circularly polarized. So now that we've discussed the properties of the beam and how they're generated, I want to discuss the dependence of the effect on the laser and plasma parameters. And to do this, we perform parameter scan using two-dimensional particle and cell simulations, which still allows for the modeling of transverse effects, but at a reduced computational, allowing for both higher resolution and a finer parameter scan. So what we do here is we fix the plasma density, and for several laser amplitudes, we vary the target thickness, where points on this plot that move towards the left are for thin targets, and points on the right of this plot are for thick targets. So what we plot here is the third harmonic efficiency as a function of the similarity parameter ND over A naught, which is again the measure of the effective charge in the target normalized to the laser amplitude. And the circles here correspond to the 2D simulations and the stars to 3D simulations, which we see here reasonable agreement between the two cases. Looking specifically at the transmitted radiation, we see that for very thick foils, there's very inefficient harmonic generation. This is because there's no clear formation of the aperture in this case, and so any harmonic generation in the transmitted direction will be filtered out by the laser. As we decrease the target thickness, though, we see a peak in the efficiency of the third harmonic at ND over A naught 0.2 or 0.3, which then subsequently decreases as the target thickness is decreased. On the other hand, in the reflected direction, what we see is that the most efficient cases take place for the thick foils. This is because for the thin foils, rapid formation of the aperture means that there will be most of the energy is going in the transmitted direction with little reflected. So now that we've done this parameter scan, we'd like to compare the more efficient regimes with the other known geometries. And so here I plot the spectral intensity as a function of the frequency for one of the more efficient cases that we just considered. And we see here that the emitted spectra follows a minus 4.6 power law, which is to be compared to the minus 3.5 spectral power law that was observed for a preformed microaperture target. You can also compare this scaling with that of a linearly polarized ultra-thin foil, which also exhibits a minus 10/3 power law scaling, which is very close to the minus 3.5 power law scaling of the preformed microaperture target. The most efficient cases for the linear polarized driving lasers takes place for thick targets, though, which you can see a minus 4/3 power law. And so with that, I'd just like to summarize now. And so we have, using particle and cell simulations, have demonstrated the generation of vortex harmonics using circularly polarized laser normally incident on a ultra-thin foil, and have shown that it is possible to achieve efficient generation in this case, which is comparable to both the linearly polarized ultra-thin foils and also to a preformed microaperture target. With that, I'd like to thank you for your time, and I'm here to answer any questions live or through the chat. Thank you.